Tonight we're going to explore something that sits at the very edge of what we can know about reality. Something that exists at a boundary so fundamental that it challenges our understanding not just of galaxies or stars, but of space and time themselves. The James Webb Space Telescope has found galaxies at distances so extreme that they represent the limit of what is physically possible to observe. These aren't just distant objects. They're signals from the edge of the observable universe, from a time when the cosmos was barely 300 million years old, from places that are now forever beyond our reach. And here's what makes this discovery so profound. These galaxies shouldn't exist. They're too big, too bright, too well-formed to have assembled in the brief time available after the Big Bang. According to our best theories about how the universe works, about how gravity pulls matter together and how stars form and how galaxies grow, these objects are impossible. Yet there they are, captured in exquisite detail by the golden mirrors of the James Webb Space Telescope, staring back at us from across 13.5 billion years of cosmic history. The most distant of these galaxies has been given the designation JADES, GSZ 140. It's a catalog number that doesn't sound particularly dramatic, but what it represents is extraordinary. This galaxy exists at what astronomers call a redshift of 14.32, which corresponds to a time just 290 million years after the Big Bang. The universe is currently 13.8 billion years old. This galaxy existed when the cosmos was only about 2% of its current age. We're seeing it in its cosmic infancy, in an era called the Cosmic Dawn, when the very first stars and galaxies were just beginning to light up the darkness. But there's a paradox here that we need to understand right from the start, because it reveals something profound about the nature of the universe itself. When astronomers measure the distance to JADES GSZ 140, carefully accounting for how space has been expanding over the eons since this galaxy emitted the light we're now detecting, they find something surprising. The galaxy is not 13.5 billion light-years away, the distance you might expect if you simply multiply the age of the universe when the light was emitted by the speed of light. Instead, it's 33.8 billion light-years away. Think about that. 33.8 billion light-years in a universe that's only 13.8 billion years old. How is that possible? Before we go any further, if you find this kind of exploration into the deepest mysteries of the cosmos fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me in being able to continue making these videos about the most profound discoveries in modern astronomy. Now let's dive into what might be the most important finding about the early universe that the James Webb Space Telescope has made. To understand the paradox of how we can see a galaxy that's 33.8 billion light-years away when the universe is only 13.8 billion years old, you need to understand something fundamental about the nature of space itself. Space is not static. It's not just an empty stage on which cosmic events play out. Space itself is dynamic. It's expanding, stretching, growing larger with every passing moment. This expansion was discovered in the 1920s by astronomer Edwin Hubble, and it's been measured with increasing precision ever since. When light from a distant galaxy begins its journey toward us, traveling at 300,000 kilometers per second, the fastest speed possible in the universe, space is expanding underneath it. As the light travels, the space between the galaxy and us continues to stretch. This has two important effects. First, it stretches the wavelength of the light itself, shifting it toward longer, redder wavelengths. This is called cosmological redshift, and it's how astronomers measure distances to very faraway galaxies. The more the light has been redshifted, the farther the galaxy and the longer the light has been traveling. Second, and this is the key to resolving our paradox, the expansion of space means that the galaxy is much farther away now than it was when the light left it. Imagine a photon, a particle of light, leaving JADES GSZ 140 290 million years after the Big Bang. At that moment, The galaxy was only about 4 billion light-years away from the location in space that would eventually become the Milky Way and Earth. The photon starts traveling toward us at the speed of light, covering distance as fast as anything in the universe possibly can. But as it travels, space itself is expanding. The distance between the photon and its starting point keeps growing, not just because the photon is moving away, but because new space is being created between them. Meanwhile, the distance between the photon and its destination, our future location, is also affected by the expansion. For the first few billion years of the photon's journey, the expansion of space was actually winning. The photon was traveling toward us, but space was expanding so fast that the distance between the photon and our location was actually increasing despite the photon's forward motion. The photon was like a swimmer trying to reach shore while being carried backward by a powerful current. Only after several billion years, as the expansion of space gradually slowed down enough, did the photon finally start making net progress toward us. It continued traveling for billions more years, covering enormous distances, while space continued to expand around it, though at a gradually decreasing rate relative to the speed of light. Finally, after 13.5 billion years of travel through expanding space, the photon reached Earth and was captured by the James Webb Space Telescope's golden mirrors in October 2023. During all that time, JADES GSZ14-0 continued to exist and evolve, though we can't see any of that evolution. We only see it as it was when the light left, 290 million years after the Big Bang. And during all that time, space continued to expand, carrying the galaxy farther and farther away from us. By now, in the present day, JADES GSZ14-0 is 33.8 billion light-years away. It's been carried away by the expansion of space to a distance that light couldn't possibly cross in the age of the universe. Astronomers use two different distance measurements to keep this straight. The comoving distance eliminates the expansion of space as a factor, measuring how far away the galaxy was when the light left it, corrected for the expansion that has occurred since. For JADES GSZ14-0, the comoving distance is about 13.5 billion light-years. The proper distance, on the other hand, includes all the expansion, measuring where the galaxy actually is right now. That's the 33.8 billion light-years figure. Here's something even more profound to consider. Because space is not just expanding but accelerating in its expansion, driven by a mysterious force called dark energy, JADES GSZ14-0 is moving away from us faster than the speed of light right now. This doesn't violate relativity because the galaxy itself isn't moving through space faster than light. Rather, the space between us and it is expanding so rapidly that the distance is growing at superluminal speeds. This means that any light leaving JADES GSZ14-0 today will never reach us. Not in a billion years, not in a trillion years, not ever. There's a boundary in space called the cosmic event horizon. Beyond this horizon, objects are receding from us so quickly due to cosmic expansion that their light can never catch up. JADES GSZ14-0 is probably beyond or very close to this horizon now. We can see it because light left it long ago when it was causally connected to us, when it was still possible for signals from that galaxy to reach our location. But its current state, what's happening there now, is forever hidden from us. The galaxy has crossed a boundary beyond which no information can ever flow to us. In a very real sense, JADES GSZ14-0 has exited our observable universe, even though we can still see its ancient light. This is what I mean when I say these galaxies exist at the edge of reality. They're at the boundary of what is physically possible for us to observe. They're among the last signals that can reach us from that part of space, from that era of cosmic history. Anything farther away, anything earlier, existed behind an impenetrable barrier. We're seeing as far back and as far away as the universe allows us to see. We're looking at the edge. The discovery of JADES GSZ14-0 began not with a dramatic observation, but with patient, systematic surveying of a tiny patch of sky. The James Webb Space Telescope's Advanced Deep Extragalactic Survey, called JADES, is a major scientific program designed to study galaxies in the early universe. Led by an international team of astronomers including Brant Robertson from UC Santa Cruz, Stefano Carniani from Scuola Normale Superiore in Italy, and many others, JADES uses both imaging and spectroscopy to identify and characterize the most distant galaxies that Webb can detect. The strategy is to first image a field of sky in multiple infrared wavelengths using Webb's near-infrared camera, called NIRCam. This creates color images where astronomers can identify candidate distant galaxies based on their colors. Galaxies at very high redshift have distinctive color signatures because their light has been stretched so much by cosmic expansion that features originally emitted in the ultraviolet and visible parts of the spectrum have been shifted into the infrared. By carefully measuring how bright a galaxy appears in different infrared filters, astronomers can estimate its redshift and determine whether it's worth following up with spectroscopy. Spectroscopy is the gold standard for confirming distances and learning about galaxies' physical properties. Webb's near-infrared spectrograph, NIRSpec, splits a galaxy's light into a rainbow of wavelengths, creating a spectrum that reveals the galaxy's chemical composition, its temperature, how fast it's forming stars, and most importantly, its precise redshift. Getting a spectrum requires much more observing time than simple imaging because you're collecting light from just one object and dispersing it across many wavelengths, so each wavelength receives only a tiny fraction of the total light. But the scientific payoff is enormous. In October 2023, Kevin Hainline from the University of Arizona was examining JADES imaging data when he noticed something unusual. Among the thousands of faint, smudgy galaxies visible in the deep field images, one object stood out. It was too bright for such a high redshift candidate. It had an unusual banana-like shape. And perhaps most puzzling, it appeared to be very close on the sky to another galaxy that was clearly much nearer to us, a foreground object billions of light-years closer. Hainline's first thought was that the bright object might be physically associated with the foreground galaxy, perhaps a region of star formation in one of its spiral arms or a satellite galaxy in orbit around it. But as he examined the data more carefully, using multiple filters and comparing images at different wavelengths, he realized something remarkable. The bright object wasn't associated with the foreground galaxy at all. It was far, far behind it, merely appearing nearby due to a chance alignment in our line of sight. The banana shape he had noticed was actually just one part of the distant galaxy, with the rest obscured by the foreground object. With this realization, the properties of the distant candidate became clearer and more puzzling. If it really was an early galaxy at high redshift, as its colors suggested, it was abnormally large and unusually bright. Hainline sent the data to his colleague Jake Helton, also from the University of Arizona, with a message saying this is seriously weird. Helton, who specializes in studying distant galaxies with Webb's Mid-Infrared Instrument or MIRI, made another surprising discovery. The candidate galaxy was not only visible in NIRCam's near-infrared images, but also detectable in MIRI's mid-infrared observations at wavelengths around 7.7 microns. This was remarkable because MIRI observes at much longer wavelengths than NIRCam. To be visible in MIRI despite being so far away meant the galaxy must be incredibly luminous, and it suggested the presence of strong emission lines, bright features in the spectrum produced by glowing gas heated by young massive stars or other energetic processes. The combination of the bright MIRI detection and the unusual properties in the NIRCam data convinced the team that this candidate deserved spectroscopic follow-up at the highest priority. In January 2024, JADES conducted what was planned to be the capstone observation of their entire program. Over 75 hours of continuous observing time, an enormous allocation for any science program, NIRSpec would obtain spectra of faint early galaxy candidates, confirming their distances and revealing their properties. The unusual bright candidate that Heinlein had found was included in this observation. The team hoped to confirm it was indeed at very high redshift, but they had no idea just how extreme the result would be. When the spectrum came back and was analyzed, there was no ambiguity. The galaxy showed a clear, unambiguous detection of the Lyman alpha break, a characteristic feature in galaxy spectra caused by hydrogen in the intergalactic medium, absorbing light at wavelengths shorter than 121.6 nanometers in the galaxy's rest frame. The position of this break in the observed spectrum allows astronomers to measure the redshift with high precision. For this galaxy, the redshift was 14.32, with an uncertainty of only plus 0.08 or minus 0.2. This made it definitively the most distant galaxy ever spectroscopically confirmed, breaking the previous record by a significant margin. The previous record holder, JADES GS-Z130, had a redshift of 13.2 and existed about 325 million years after the Big Bang, only 35 million years later than the new discovery. Cosmically speaking, 35 million years is not a huge difference. The universe doesn't evolve dramatically over such relatively short timescales. But the properties of these two galaxies turned out to be vastly different, and that difference is what makes JADES GS-Z140 so significant and so puzzling. JADES GS-Z130 is faint and compact, appearing as a small smudge in Webb's images. Its spectrum shows it's forming stars, but at a modest rate, and its total stellar mass is relatively low. It's essentially what astronomers expected to find at such early times based on their theoretical models and computer simulations of galaxy formation. JADES GS-Z140, on the other hand, is neither faint nor compact. It's extraordinarily bright, intrinsically luminous enough that it would be visible to Webb across even greater cosmic distances if such distances were accessible. And it's extended, spanning about 1,600 light-years in diameter. For comparison, that's about 1% the size of the Milky Way, but recall that the Milky Way has had 13.6 billion additional years to grow. The brightness of JADES GS-Z140 is particularly noteworthy. In a young universe, there are two main ways a galaxy can be bright. It can contain many luminous young stars actively forming and shining brightly, or it can host a supermassive black hole at its center, with material falling into the black hole releasing enormous amounts of energy as it forms an accretion disk and produces a quasar. Quasars are among the brightest objects in the universe, often outshining their entire host galaxies. Many distant luminous galaxies that astronomers have found turn out to be quasars rather than pure stellar systems. But the large extended size of JADES GS-Z140 clearly indicated that most of its light was coming from stars distributed across the galaxy, rather than from a compact central source. Daniel Eisenstein from the Center for Astrophysics noted in a statement that the size of the galaxy clearly proves that most of the light is being produced by large numbers of young stars, rather than material falling onto a supermassive black hole in the galaxy's center, which would appear much smaller. This means we're seeing a galaxy that has already assembled hundreds of millions of stars, possibly several 100 million solar masses worth of stellar material, in only 290 million years after the Big Bang. This is where the galaxy violates our theoretical expectations. According to the lambda CDM model, the standard model of cosmology that has successfully explained so many aspects of the universe's structure and evolution, early galaxy formation should proceed through a bottom-up hierarchical process. First, Small dark matter halos form from slight overdensities in the primordial universe. These halos gravitationally attract normal matter, primarily hydrogen and helium gas left over from the Big Bang. The gas falls into the halos, condenses, and begins forming the first stars. These first-generation stars are thought to be very massive, perhaps hundreds of times the mass of the Sun, and they burn through their fuel quickly, exploding as supernovae after only a few million years. Their explosions seed the surrounding gas with heavier elements, carbon, oxygen, nitrogen, iron, elements that didn't exist in the primordial universe but are created in stellar interiors and supernova blasts. This enriched gas forms the next generation of stars. Over time, small galaxies merge together to form larger ones. The process continues hierarchically, with progressively larger structures assembling from smaller building blocks over hundreds of millions or billions of years. According to this framework, you shouldn't get a large, bright, massive galaxy like JADES GSZ14-0 until at least a billion years after the Big Bang, possibly longer. There simply isn't enough time for the hierarchical assembly process to produce such an object. The dark matter halos haven't had time to grow large enough through mergers. The gas hasn't had time to cool and condense efficiently enough. The stars haven't had time to form in sufficient numbers. Every step in the process has a characteristic timescale set by physics, by the strength of gravity, by the rate at which gas can radiate away energy and collapse, by the lifetimes of massive stars. When you add up all these timescales, you don't get JADES GSZ14-0 at 290 million years. You get something much smaller and fainter, something like JADES GSZ13-0. The spectrum of JADES GSZ14-0 revealed other surprising properties that deepen the mystery. The galaxy's light is not as blue as astronomers expected for such an early galaxy. In a very young galaxy filled with massive hot stars and no dust, the spectrum should be very blue, dominated by ultraviolet light from those hot stars that has been redshifted into the infrared by the time it reaches us. But JADES GSZ14-0 shows reddening, indicating the presence of dust. Cosmic dust, tiny particles of carbon, silicon, and other elements, absorbs and scatters blue light more effectively than red light, causing sources behind it to appear redder. The fact that this galaxy already contains dust means that generations of stars must have lived and died, creating heavy elements and casting them out into space where they condensed into dust grains. This takes time, yet it has apparently happened in less than 300 million years. Jake Helton's analysis of the MIRI detection provided further evidence for this rapid enrichment. The MIRI data showed emission at 7.7 microns that was brighter than expected based on extrapolating from the NIRCam measurements. This excess brightness indicated the presence of strong emission lines, bright narrow features in the spectrum caused by specific transitions in atoms and ions. Analysis suggested these were likely emission from ionized oxygen and hydrogen, produced in regions of intense star formation, where massive stars are irradiating surrounding gas clouds. The presence of oxygen is particularly significant because oxygen, the third most abundant element in the universe today, is produced primarily in the cores of massive stars and released when they explode. Finding oxygen in JADES GSZ14-0 confirms that multiple generations of massive stars have already completed their life cycles. In March 2025, astronomers using the Atacama Large Millimeter Array, ALMA, a powerful radio telescope in Chile, announced the detection of oxygen in JADES GSZ14-0, confirming the indirect evidence from Webb's observations. This marked the most distant detection of oxygen ever made, seeing this element when the universe was only 2% of its current age. The ALMA observations measured the specific wavelength of a radio transition of ionized oxygen, providing independent confirmation of the galaxy's redshift, and revealing the presence of this heavy element in the early cosmos. Stefano Carniani, who led the spectroscopic analysis for the JADES team, emphasized just how unprecedented this discovery was. He stated that all of these observations together tell us that JADES GS-Z14-0 is not like the types of galaxies that have been predicted by theoretical models and computer simulations to exist in the very early universe. Given the observed brightness of the source, we can forecast how it might grow over cosmic time, and so far we have not found any suitable analogs from the hundreds of other galaxies we've observed at high redshift in our survey. Brant Robertson, the lead author on the first paper announcing the discovery, noted that this discovery is completely unanticipated and is likely to be seen as the most significant extragalactic discovery with JWST to date. This demonstrates the immediate impact new JWST observations can have on our knowledge of the distant universe. Ben Johnson from the Center for Astrophysics added that JADES GS-Z14-0 shows that galaxy formation in the early universe was very rapid and intense, and that JWST will allow us to find more of these galaxies, perhaps when the universe was even younger. And find more galaxies they have. JADES GS-Z14-0 was not discovered alone. In the same observations, the team identified JADES GS-Z14-1, another galaxy at nearly the same distance, with a redshift of about 14.18. This second galaxy is slightly less distant, existing about 20 million years later in cosmic time than JADES GS-Z14-0, but it's still among the most distant galaxies ever confirmed. The fact that two such galaxies were found in the same relatively small field of sky has profound implications. The JADES team observed a region near the Hubble Ultra Deep Field, one of the most studied patches of sky in all of astronomy. The field covers an area about the size of a grain of sand held at arm's length. It's an incredibly tiny fraction of the entire sky. Yet in this tiny region, they found two galaxies at redshifts around 14, far more than statistical predictions based on previous observations suggested should exist. If two such galaxies exist in this small field, how many must exist across the entire sky? Extrapolating from this finding, astronomers estimate there must be a large population of bright galaxies in the early universe, far more than the lambda CDM model predicts. A separate JADES study, led by Brant Robertson, analyzed the statistics of galaxy abundances at high redshift and concluded that the observed number of bright galaxies at redshifts greater than 10 is about 10 times higher than predicted by models based on observations before Webb. This isn't a small discrepancy that can be dismissed as a statistical fluke. It's a fundamental mismatch between theory and observation. The implications of this discrepancy extend beyond just the number counts. If these bright massive galaxies are common in the early universe, then our understanding of how structure forms after the Big Bang must be revised. Perhaps the initial density fluctuations in the primordial universe were larger than we thought, seeding the formation of massive structures earlier. Perhaps the first stars formed more efficiently than we assumed, converting a higher fraction of available gas into stars. Perhaps there are feedback mechanisms we don't understand that accelerate the assembly of galaxies. Perhaps dark matter behaves differently in the early universe than it does today. Or perhaps the lambda CDM model itself needs modification in ways we haven't yet imagined. Let's zoom out for a moment and talk about what we actually mean by the observable universe and why these distant galaxies represent such a fundamental boundary. The observable universe is not the entire universe. It's just the portion from which light has had time to reach us since the Big Bang. Because the universe is 13.8 billion years old and light travels at a finite speed, there's a maximum distance from which we can receive signals. Beyond that distance, light simply hasn't had time to make the journey yet. But it's more complicated than that because of cosmic expansion. The boundary of the observable universe is not simply 13.8 billion light-years away. If space were static, that would be true. A photon traveling at the speed of light for 13.8 billion years would cover 13.8 billion light-years. But space has been expanding the entire time, carrying distant objects farther away even as their ancient light travels toward us. When you account for this expansion, the proper distance to the edge of the observable universe, the edge of what we can theoretically see, is about 46.5 billion light-years. This creates an observable universe about 93 billion light-years in diameter. JADES GSZ14-0 at 33.8 billion light-years proper distance is not quite at this absolute edge, but it's remarkably close, about 73% of the way to the horizon. The fact that Webb can detect and characterize a galaxy at this distance is a testament to the power of the telescope and the sensitivity of its instruments. But there's another boundary we need to consider, one that's more subtle but perhaps even more profound than the edge of the observable universe. It's called the cosmic event horizon, and it represents the limit of what we can ever possibly observe. Not just what we can see now, but what we could see given infinite time in the future. The cosmic event horizon exists because the expansion of the universe is accelerating, driven by dark energy. In a universe where expansion was slowing down or even constant, photons from arbitrarily distant galaxies would eventually reach us given enough time. But in an accelerating universe, there's a distance beyond which galaxies are receding so fast that light leaving them now will never catch up to us despite traveling at the speed of light. The expansion of space is carrying them away faster than light can close the gap. Current estimates place the cosmic event horizon at about 16 billion light-years moving distance. Beyond this horizon, events occurring now will never be observable to us no matter how long we wait. The galaxies beyond this boundary are causally disconnected from us. They've exited our observable universe not just in practice, but in principle. They're beyond the edge of reality as far as we're concerned because no information from them can ever reach us. JADES GSZ14-0 with a moving distance of about 13.5 billion light-years is approaching this event horizon. The galaxy we see in Webb's images existed 290 million years after the Big Bang, when it was still causally connected to us, when it was still possible for its light to reach us eventually. But in the 13.5 billion years since that light left, the galaxy has been carried by cosmic expansion to a much greater distance, likely beyond the event horizon by now. Anything happening in JADES GSZ14-0 today, any stars forming, any supernovae exploding, any planets that might be forming around those stars, all of it is forever hidden from us. This is a sobering realization. We can see JADES GSZ14-0 as it was, but we can never see it as it is. We can observe one brief snapshot from its youth, but we will never know how its story continues. We're seeing the opening chapter of a cosmic narrative whose subsequent pages are closed to us by the fundamental structure of spacetime itself. The galaxy exists now, presumably evolved into something larger and more complex, but it exists in a region of space that is disconnected from ours. It has passed beyond a boundary that can never be crossed. There's something deeply philosophical about this realization. It means there are limits to knowledge that are not imposed by technology or resources, but by the laws of physics themselves. No matter how powerful our future telescopes become, no matter how much we advance our understanding of the cosmos, we can never observe the current state of JADES GSZ14-0 or galaxies like it. We can only ever see their ancient light, the signals they sent when they were young, and the universe was small enough that information could still flow between distant regions. The discovery of JADES GSZ14-0 and other extreme early galaxies has sparked intense debate among cosmologists about what might need to change in our theoretical framework. The Lambda CDM model has been incredibly successful at explaining a wide range of observations, from the large-scale structure of the universe to the detailed pattern of fluctuations in the cosmic microwave background radiation. But it makes specific predictions about the early universe that now appear to be in tension with what Webb is seeing. One possibility is that the initial conditions of the universe, the density fluctuations that seeded all structure formation, were different than we thought. Perhaps there were rare regions where the density was significantly higher than average, creating deeper gravitational wells that could assemble galaxies more quickly. Computer simulations of structure formation typically use statistical models of these initial fluctuations based on measurements of the cosmic microwave background. But those measurements average over large scales. Perhaps there's more small-scale structure, more variation in density on the scales of individual galaxies than the models assume. Another possibility relates to the formation of the first stars. These stars, called population III stars, because they would have contained no heavy elements beyond the trace amounts of lithium created in the Big Bang, have never been directly observed. All stars we've studied contain at least some heavy elements because they formed from gas that had been enriched by previous generations of stars. Population III stars exist only in theory and in computer simulations. But their properties matter enormously for understanding the early universe because they were the first objects to light up the cosmic dark ages, the first sources of light after the Big Bang. Theoretical models suggest population III stars should be very massive, perhaps hundreds of times the mass of the Sun, because the primordial gas from which they formed had no heavy elements to help it cool efficiently. In modern star-forming regions, dust and molecules made of heavy elements radiate energy very effectively, cooling gas clouds and allowing them to fragment into many smaller clumps that become individual stars. Without these coolants, primordial gas can only cool through atomic hydrogen radiation, which is less efficient. This leads to higher temperatures during collapse and favors the formation of very massive stars. These massive population III stars would burn through their fuel in only a few million years, then explode as supernovae, enriching the surrounding gas with the first heavy elements. If the population III star forming efficiency was higher than theoretical models suggest, if more of the available gas was converted into these first stars, then the enrichment process would proceed more quickly and subsequent generations of stars could form faster and more efficiently. This might help explain how galaxies like JADES, GSZ14-0 assembled so quickly. Some researchers have proposed that the physics of star formation itself might be different in the early universe due to the higher gas densities, the lack of heavy elements, or the stronger radiation backgrounds from all the newly forming stars. Perhaps stars formed faster or more efficiently under these conditions. Perhaps the initial mass function, the distribution of stellar masses at birth, was different, favoring massive stars that live and die quickly and produce heavy elements rapidly. These are all active areas of research where better observations from Webb are constraining the possibilities. There's also the possibility that our understanding of dark matter needs revision. The Lambda CDM model assumes dark matter is cold, meaning the particles move slowly relative to cosmic expansion and can clump together efficiently under gravity to form structure. But we still don't know what dark matter actually is. We've never detected a dark matter particle directly despite decades of increasingly sensitive experiments searching for them. If dark matter has properties we haven't accounted for, if it interacts with normal matter or with itself in ways beyond pure gravity, then structure formation could proceed differently than the standard models predict. Some theorists have suggested that in the early universe, dark matter might have been warmer, with particles moving faster, which would suppress the formation of the smallest structures, but potentially enhance intermediate-scale structures at just the right mass scales to explain the observed early galaxies. Others have proposed that dark matter undergoes some kind of phase transition in the early universe, changing its properties over time. These ideas are speculative, but they're being seriously considered in light of the Webb observations. Another radical possibility that's gained attention is that the lambda CDM model's assumption of a cosmological constant, the lambda in its name, representing a constant dark energy density throughout cosmic history, might be wrong. Perhaps dark energy was different in the early universe, maybe weaker or even absent, allowing structure to form more efficiently before the accelerating expansion took over. This would require modifying Einstein's general theory of relativity, or introducing new fields beyond those in the current standard model of particle physics. It's a big step, but the discrepancy between prediction and observation might be significant enough to justify considering such modifications. What makes all of this particularly exciting from a scientific perspective is that we're not just speculating. We have the data. Webb is providing detailed observations of the early universe that can test these different ideas. Each new galaxy discovered, each spectrum obtained, each measurement of the abundance and properties of early galaxies adds constraints that models must satisfy. The interplay between observation and theory is happening in real time, and it's driving rapid progress in our understanding. Let's talk about some of the other remarkable galaxies Webb has found in the early universe, because JADES GS-Z140 is just the tip of the iceberg. One of the most intriguing is a galaxy called GNZ11. This galaxy was actually first discovered by the Hubble Space Telescope back in 2016, identified as one of the most distant galaxies known at that time. Hubble observations suggested it existed about 430 million years after the Big Bang, making it an important target for Webb's more powerful instruments once they came online. When Webb turned its attention to GNZ11, the results were stunning. The near-infrared spectrograph obtained a detailed spectrum showing that the galaxy contains a supermassive black hole at its center. The black hole is about 2 million times the mass of the Sun, and it's actively feeding, accreting material and shining as a quasar. Finding such a massive black hole so early in cosmic history is remarkable because we don't fully understand how supermassive black holes form and grow. In the nearby universe, essentially all large galaxies contain supermassive black holes at their centers, ranging from millions to billions of solar masses. Our own Milky Way hosts a black hole of about 4 million solar masses. But how do these black holes become so massive? If they start as stellar mass black holes, the remnants of massive stars that collapse and explode as supernovae, they need to grow by accreting material and merging with other black holes. Accretion has a maximum rate, called the Eddington limit, set by the balance between gravitational attraction pulling matter in and radiation pressure pushing it out. For a black hole to grow from 10 solar masses, typical of a stellar remnant, to 2 million solar masses in only a few hundred million years would require it to accrete at or above the Eddington limit continuously. This is possible but requires special conditions, a steady supply of gas and efficient accretion. The presence of a 2 million solar mass black hole in GNZ11 suggests either that supermassive black holes can grow extremely rapidly in the early universe, possibly through super-Eddington accretion, where material somehow falls in faster than the theoretical limit allows, or that they form through alternative mechanisms that create more massive seeds to begin with. One possibility is direct collapse black holes, where a gas cloud collapses directly into a black hole of thousands or tens of thousands of solar masses without going through the stellar evolution stage. This would give black holes a head start, requiring less time to grow to the millions of solar masses we observe. The spectrum of GNZ11 revealed another remarkable feature. It shows signs of population III stars, those first-generation stars made purely of hydrogen and helium with no heavy elements. Specifically, The spectrum contains emission from a helium ion that requires extremely energetic radiation to create, more energetic than what's typically produced by normal stars. This emission is consistent with the presence of very hot, very massive stars that would have been the first generation. If confirmed, this would represent the first indirect detection of population III stars, giving us a window into the very first stellar populations that lit up the universe. Roberto Maialino, one of the lead researchers studying GNZ11, stated that the discovery of these signatures represents the first clear detection of population III stars in any galaxy, a major breakthrough in our understanding of the earliest cosmic epochs. Beyond JADES GSZ14-0 and GNZ11, Webb has been finding bright, massive early galaxies everywhere it looks. A survey led by Ivo Lab and collaborators found a group of galaxy candidates they called Glass Z and CERS, some with estimated stellar masses reaching 10 billion solar masses at redshifts around 10 to 11. These would be comparable in mass to present-day massive galaxies, but existing when the universe was only 500 million years old. The team nicknamed these objects universe breakers because their properties seem to break our models of cosmic evolution. While some of these candidates turned out upon detailed spectroscopic study to be less massive or at slightly lower redshifts than initially estimated, they're still remarkably massive for their epochs and contribute to the overall pattern of surprisingly abundant bright early galaxies. The Cosmic Evolution Early Release Science Survey, known as CERS, has also found numerous bright galaxies at high redshift. Steve Finkelstein from the University of Texas at Austin, who leads CERS, has compiled catalogs of hundreds of galaxy candidates at redshifts above 7 and dozens at redshifts above 10. Each of these galaxies represents a data point testing our models. Each one that's brighter or more massive than predicted adds to the pressure on theoretical frameworks to explain what's happening in the early universe. The pattern is clear and consistent across multiple independent surveys using different fields of sky and different observing strategies. The early universe is more active, more developed, more populated with substantial galaxies than anyone predicted before Webb launched. Another fascinating finding comes from studies of galaxy sizes and morphologies at high redshift. When Hubble looked at distant galaxies, they appeared as faint smudges, barely resolved even with Hubble's excellent imaging capabilities. Webb's sharper infrared vision reveals that many early galaxies have distinct structures. Some are elongated and irregular, showing signs of ongoing mergers or turbulent dynamics. Others, surprisingly, show disk-like structures suggesting rotation and organized motion. Finding rotationally supported disks at such early times suggests that galaxies can settle into coherent configurations faster than models anticipated. This again points toward more rapid and efficient assembly processes in the early universe. There's also evidence emerging from massive clumps of star formation within early galaxies. Instead of stars forming smoothly throughout the galaxy, they form in giant, concentrated regions hundreds or thousands of light years across where gas has collapsed under gravity and ignited furious bursts of star formation. These clumps are thought to migrate inward over time due to dynamical friction, potentially building up the central bulges of galaxies or feeding central black holes. Finding such clumpy structures at high redshift fits with theoretical predictions about how turbulent gas behaves in the early universe. But the masses and sizes of the clumps are often larger than simulations predicted. The James Webb Space Telescope has also revolutionized our understanding of galaxy mergers in the early universe. Mergers between galaxies are thought to be a key driver of growth, with smaller galaxies combining to form larger ones. Webb's sensitivity allows it to detect galaxy pairs and groups at high redshift, revealing the frequency and characteristics of mergers during cosmic dawn. Some observations show galaxies in the process of merging, with tidal tails of stars and gas being pulled out by gravitational interactions. These mergers are clearly happening, supporting the hierarchical growth picture, but the question is whether they can happen fast enough and efficiently enough to build the massive galaxies we observe. One of the key insights from Webb's observations is that the star formation efficiency in early galaxies appears to be higher than in galaxies today. When astronomers measure how much molecular gas a galaxy contains and how rapidly it's forming stars, they can calculate the star formation efficiency, essentially what fraction of available gas is being turned into stars per unit time. In nearby galaxies, typical efficiencies are such that it takes about 1 billion years to convert the gas into stars. In early galaxies observed by Webb, efficiencies appear to be higher, with much shorter timescales. This suggests that conditions in the early universe favored rapid star formation, possibly due to higher gas densities, different turbulence properties, or other environmental factors that we're only beginning to understand. Let's talk about the concept of cosmic variance, which is relevant to interpreting all these findings. When we observe a small region of sky, we're seeing a particular sample of the universe that might not be perfectly representative of the average. By chance, we might be looking at a region that happens to have more galaxies, or fewer, or different types than the cosmic average. This is called cosmic variance, and it's a source of uncertainty in all surveys that don't cover enormous areas of sky. The fields observed by JADES, CEERS, and other Webb programs are relatively small, covering fractions of a square degree. This means there's some possibility that they're seeing unrepresentative patches of the universe, perhaps overdense regions where more galaxies formed than average. However, the fact that multiple independent surveys looking at different fields are all finding similar overabundances of bright early galaxies suggests this isn't just cosmic variance. If it were, we'd expect some fields to show more galaxies and others fewer, averaging out to the predicted number. Instead, essentially all deep Webb observations are finding more bright galaxies than expected. This consistency across different lines of sight strongly suggests we're seeing a real effect, a genuine departure from theoretical predictions, rather than just statistical flukes. As Webb continues observing and more data accumulates, astronomers are building up larger samples of early galaxies that will reduce the uncertainties from cosmic variance. The longer Webb operates, the more fields it observes, the more robust the statistical conclusions will become. But already, with just 2 years of science operations, the pattern is clear enough that theorists are taking it seriously and working to revise their models. Some researchers estimate that with current detection rates, Webb will eventually catalog thousands of galaxies at redshifts above 7 and hundreds at redshifts above 10, providing an unprecedented data set for studying the early universe. There's an exciting prospect that Webb might eventually detect galaxies at even higher redshifts than JADES GSZ 14-0. The telescope's capabilities extend potentially to redshifts of 20 or higher, corresponding to times as early as 150 million years after the Big Bang. At such early times, we'd be seeing the universe in its true infancy, when the first stars and galaxies were just beginning to form and the cosmic dark ages were ending. Whether galaxies exist at these extreme redshifts is an open question. Theoretical models suggest the first stars began forming around redshift 20 to 30, but whether they had assembled into anything we'd recognize as a galaxy by that time is uncertain. If Webb does detect a galaxy at redshift 20, it would be even closer to the absolute earliest possible epoch of galaxy formation than JADES GSZ 14-0. It would push the boundary of our observations even nearer to the edge of what's physically possible to see. Such a discovery would provide invaluable constraints on models of the first stars and the reionization of the universe, the process by which ultraviolet radiation from early stars and galaxies ionized the neutral hydrogen gas that filled space. Reionization is one of the major phase transitions in cosmic history, marking the end of the Dark Ages and the beginning of the modern universe where most hydrogen is ionized. Webb observations at the highest redshifts probe this transition directly. Looking ahead to the future of this research, several exciting developments are on the horizon. The Nancy Grace Roman Space Telescope, a NASA mission currently scheduled to launch in the early 2030s, will complement Webb's deep-pointed observations with wide-field surveys. Roman will be able to image much larger areas of sky than Webb, though not quite as deeply, allowing it to find rare objects and map the distribution of galaxies over large scales. By combining Webb's depth with Roman's area coverage, astronomers will be able to build a complete census of early galaxies, understanding not just what exists in small fields, but how galaxies are distributed across the cosmos. Ground-based telescopes are also advancing rapidly. The next generation of extremely large telescopes, including the 30-meter telescope and the European Extremely Large Telescope, will have mirrors much larger than Webb's, collecting more light and achieving sharper resolution at optical and near-infrared wavelengths where they can operate from the ground. These telescopes will be able to obtain extremely detailed spectra of high redshift galaxies, measuring their chemical compositions, dynamics, and physical properties with unprecedented precision. They'll also be able to study fainter objects around bright galaxies, detecting satellite galaxies and extended halos that Webb might miss. The Atacama Large Millimeter Array continues to play a crucial role by observing at radio wavelengths where it can detect emission from coal dust and molecules like carbon monoxide. These observations trace the cold gas reservoirs from which stars form, complementing Webb's observations of the stars themselves. ALMA's detection of oxygen in JADS GS Z14-0 is just the beginning. Future ALMA observations will measure the masses of gas reservoirs in many early galaxies, determine how gas is distributed within them, and track the flow of material from the intergalactic medium into galaxies, and from galaxies into circumgalactic halos. This will provide a complete picture of the baryon cycle in the early universe. The Square Kilometre Array, currently under construction in South Africa and Australia, will eventually be the world's most sensitive radio telescope. It will be able to detect the 21-centimeter line of neutral hydrogen directly from the high redshift universe, mapping the distribution of gas before and during the epoch of reionization. SCA observations will show where the neutral hydrogen was and how it became ionized as the first galaxies turned on. This will provide the environmental context for understanding early galaxy formation, revealing which regions of space had more gas available for galaxies to accrete, and which regions were already ionized by earlier generations of stars. Theoretical work is also advancing rapidly in response to Webb's observations. Cosmologists are running new suites of computer simulations with higher resolution and more sophisticated physics to try to reproduce what Webb is seeing. These simulations must include detailed treatments of star formation, supernova feedback, black hole growth and feedback, chemical enrichment, radiative transfer of ultraviolet photons through gas, and many other physical processes. Getting all of this right is enormously computationally expensive, but modern supercomputers are finally becoming powerful enough to run simulation that can match Webb's observational capabilities. Some simulation groups are exploring modifications to the standard Lambda CDM framework, testing whether alternative dark matter models or modified gravity theories can explain the observations better. Others are focusing on improving the subgrid models that describe processes like star formation efficiency and supernova feedback that occur on scales smaller than the simulation can directly resolve. Still others are trying to understand the population of early galaxies statistically, asking what distribution of properties and what range of formation histories could produce the observed number counts and brightness distributions. There's also theoretical work on alternative interpretations of the observations. Could some of the bright early galaxies be misidentified? Could they actually be at lower redshifts, but with unusual spectra that mimic high redshift signatures? Detailed spectroscopic follow-up makes this unlikely for well-studied objects like JADES GSZ140, but for some of the photometric candidates identified only through imaging without spectroscopy, misidentification remains possible. Understanding the false positive rate and ensuring that claimed high redshift galaxies are real is an important part of the ongoing research. As we contemplate these discoveries and what they mean, it's worth reflecting on the deeper implications. We're living through a golden age of cosmology where powerful new instruments are revealing aspects of the universe that were completely inaccessible just a few years ago. The James Webb Space Telescope has given us vision into the cosmic past that previous generations could only dream about. We're seeing the universe's first galaxies, the first generations of stars, the formation of the first black holes. We're witnessing cosmic dawn, the moment when light began to fill the darkness and the universe began to take on its modern appearance. These observations are doing more than just cataloging distant objects. They're testing fundamental theories about how the universe works, about the nature of dark matter and dark energy, about the laws of gravity and the behavior of matter under extreme conditions. When we find that observations don't match predictions, when galaxies exist that shouldn't according to our best theories, it tells us that our understanding is incomplete. There are pieces of the puzzle we're missing. There are processes we haven't accounted for. There are perhaps even new physics waiting to be discovered. This is how science progresses. Observation and theory engage in a dialogue. Theory makes predictions. Observations test those predictions. When they disagree, something has to give. Either the observations are wrong, which requires careful checking and independent verification, or the theory is wrong, which requires revision and extension. In this case, the observations from multiple independent teams using the world's most powerful telescope are robust. The theory, therefore, must adapt. We're in the early stages of that adaptation right now, and it's an exciting time to be following along. There's also something profound about the fact that we're seeing these galaxies at all. The light from JADES GSZ140 has been traveling toward us for 13.5 billion years. It left that galaxy when the universe was brand new and has been crossing the expanding cosmos ever since. For all that time, the photons carried information about their source, information about the stars and gas and dust that emitted them. They traveled through intergalactic space, through regions where no stars shine and matter is spread incredibly thin, just a few atoms per cubic meter on average. They passed by or through other galaxies, gravitationally lensed by massive structures, their paths bent slightly by the curvature of spacetime. They survived essentially unchanged despite the incredible journey because photons don't age or decay. A photon is the same at the end of its journey as at the beginning. The only thing that changes is its wavelength, stretched by the expansion of space. That stretching is what tells us where and when the photon came from. It's a message encoded in the light itself, a timestamp marking the epoch when it was emitted. And finally, after all those billions of years, those photons entered Webb's mirrors, were focused onto its detectors, and their information was recorded and transmitted to Earth, where scientists analyzed it and reconstructed what JADES GSZ140 looked like nearly at the beginning of time. This is one of the great achievements of human civilization. That we can do this, that we can intercept ancient light from the edge of the universe and decode what it's telling us, is remarkable. It requires not just the technology to build Webb, but the scientific framework to interpret what we're seeing, the physics and mathematics to model cosmic expansion and galaxy formation, the chemistry to understand stellar spectra, the astronomy to operate telescopes and analyze data. It's a cumulative achievement built on centuries of scientific progress, on the work of countless researchers who developed the theories and techniques that make this possible. Standing on all those shoulders, we can now look to the very edge of reality and see what's there. If you've made it this far through this deep exploration of some of the most distant objects in the universe, I hope you've gained not just knowledge, but a sense of wonder at what we're discovering and how we're discovering it. These galaxies at the edge of the observable universe are more than just astronomical curiosities. They're fundamental probes of the cosmos, testing our deepest theories about how everything began and how structure emerged from the smooth fireball of the Big Bang. They're also reminders of how much we still have to learn, how many mysteries remain unsolved, how much our understanding continues to evolve as new observations challenge old assumptions. If your mind has been expanded by learning about these impossible galaxies at the edge of reality, if you're excited to follow along as this story continues to unfold, then please hit that like button and subscribe to the channel. We're living in an extraordinary era of astronomical discovery. Webb is only 2 years into what will hopefully be decades of operation, and already it's revolutionizing our understanding of the early universe. There will be many more discoveries to come, many more surprises, many more moments where observations challenge theory and force us to rethink what we thought we knew. You won't want to miss what comes next. Leave a comment below and share your thoughts. Does it surprise you that we can see galaxies at such enormous distances? Do you find it remarkable that we're observing light that's been traveling for longer than Earth has existed? What do you think about the fact that these galaxies are now forever beyond our reach, that we can see their past but never their present? How do you think cosmologists will resolve the tension between these observations and the lambda CDM model? The universe has been speaking to us through these ancient photons, carrying messages from the edge of space and time. We've been learning to read those messages, to decode the information they carry, and what they're telling us is simultaneously thrilling and humbling. Thrilling because we're seeing things no one has seen before, pushing the boundaries of observation to limits that seemed impossible just a few years ago. Humbling because the universe continues to surprise us, to present phenomena that challenge our theories and force us to admit how much we still don't understand. These galaxies at the edge of reality represent both a triumph of human knowledge and a reminder of its limits. We've developed the technology and the theoretical framework to detect and study them. We understand that we're seeing them as they were 13.5 billion years ago, that their light has traveled across an expanding universe to reach us, that they're now far beyond our cosmic horizon. But we still can't fully explain how they formed so quickly, what processes assembled them so efficiently, what this tells us about the fundamental workings of the cosmos. We're at a frontier, and frontiers are always exciting because they're where the known meets the unknown, where answers give way to questions, where what we've learned reveals how much more there is to learn. So as we conclude this exploration of the edge of the observable universe, remember that right now, at this very moment, there are photons traveling through space that left distant galaxies billions of years ago and are on their way to us. Some of them will arrive tomorrow or next week or next year and will be captured by Webb or other telescopes, adding to our growing understanding of the early universe. Some will tell us about galaxies even more distant than JADES GS Z14-0, if such galaxies exist at redshifts Webb can detect. Some will show us new phenomena we haven't seen before, new types of objects or new physical processes at work in the infant cosmos. The journey of discovery continues, and we're privileged to be alive at a time when we have the tools to observe the universe's earliest moments and the scientific framework to begin understanding what we see. Our descendants will look back at this era as the time when humanity first truly saw cosmic dawn, when the veil was lifted and the infant universe became visible for the first time. They'll study these early Webb observations, the way we study Galileo's first telescope observations or Hubble's discovery of cosmic expansion, as foundational moments in the history of astronomy. Thank you for joining me on this journey to the edge of reality. If you found this exploration valuable and thought-provoking, please take a moment to like this video and subscribe to the channel so you don't miss future explorations of the cosmos. We're living through a golden age of astronomical discovery, and the best may still be yet to come. The universe is vast, strange, and wonderful, full of mysteries waiting to be revealed. And every time we point our telescopes at the sky, we take one more step toward understanding our place within it. Good night, and may your sense of wonder at the cosmos never fade. Somewhere out there at the edge of space and time, ancient galaxies shine with the light of their youth, sending signals across the expanding universe. Some of those signals have reached us, captured by our telescopes, decoded by our instruments, contemplated by our minds. We've seen to the edge of reality and found that the universe is stranger, more active, more complex than we imagined. And that's exactly what makes it worth exploring. The journey continues, and the edge keeps receding as our understanding deepens. There will always be more to discover, more to learn, more to wonder about. That's the beauty of science and the grandeur of the cosmos we're privileged to explore.